Welcome back to the Intro to Houdini Carbon Nanotube mini-series. This is a part 5, so if you're completely brand new and you want to check out part 1, there's a link up in the pop-up up here and also in the video description. So let's just jump right into Houdini and get started. So to review, last time we learned how to make our nanotube grow using keyframe animation. And I'll put a starting file with this nanotube here, a link to that in the video description as well, so you can download that and follow along if you don't have your own already. Basically what we did, if we jump into this nanotube, is we used a linear animation. I'm going to open up the animation editor. Here, we'll open up the animation editor here. So we spent a long time talking about animation and animation curves and tangents and all of that sort of stuff, and we made this linear animation on this carve node, which trims a curve starting short and then growing longer, and then that nanotube model gets mapped onto that. And we made a little proxy switch so that we can easily switch between our full model, which is a little bit heavier to compute, and a much more simplified tube version of it. In this lesson, we're going to be setting up a slightly more complicated system for animation so that it will work for a whole field of nanotubes, which is the ultimate goal. We want dozens or even hundreds of nanotubes, and we don't want to key them all by hand. So the system that we're going to create in this video is going to let us do that much more easily. This is going to involve digging a little bit more into attributes, which we've mentioned in the past, and learning a little bit about Houdini's embedded programming language, which is called VEX. So I hope this tutorial doesn't vex you too much. I'm sure that joke has never ever been made before. And we're going to be fixing these little dangling bonds that we mentioned in the last video to trim those off. But first, attributes. So I'm going to set aside the nanotube for a few minutes here, and I'm going to create not a soccer ball, but a platonic solid, which we will use the soccer ball for. Put the display flag on here and space F to frame up. So you might remember in one of the first lessons, we talked a little bit about geometry components. So I'm going to open up the geometry spreadsheet here, new pane tab type, inspectors geometry spreadsheet. So you might recall from that previous video that various geometry components can have attributes. So the points here, which we can highlight here, these blue dots, they each have a position in X, Y, and Z. That's a 3-part attribute called a vector attribute. And the short form of that is just the letter capital P. The primitives have a color attribute. The name for that is capital C, lowercase d, CD. And some of these have the value 1, some of these have the value 0 for white and black respectively. There are some other built-in attributes, but really the beauty of this is that you can create any kind of data that you want to. So let's do some examples here, and a really great way of showing some test data is to work with a grid. So I'm going to put the display flag on that here, and now we've got a 10 by 10 set of points with primitives between them. So you can see that the primitives don't have any attributes to start out with, but the points have their point data, and they all have 0 for y, if that makes sense. So let's play with this grid a little bit. What I'm going to do is actually going to create a sphere and copy that sphere onto every single point of this grid. So we've seen how to do that. We can use the copy 2 points node, drop that down, and the geometry that we want to copy is the sphere, and the points that we want to copy them to is the grid, and we'll put the display flag on here. And our sphere is way too big, so we're going to put our uniform scale down to something like 0.4. So a really cool thing about the copy to points is that not only does it copy the geometry to each of the points, but it can actually grab attributes from the grid points and apply them to the copies. What does that look like? So for example, if each of these points had a different color, the sphere would take on that color. So when we want to create a new attribute, we can use a node called create attribute or attribute create. I'll just start typing attribute, and we get our attribute create. Put that in here. So we have a few things to do to set this up for color. Remember the name of the attribute that we want is capital C, lowercase d. That means color. And you can see that by default, the default value is 000, and that is black. But we want to be a little bit more specific about how we're setting this up. So the size of this attribute is actually 3 different numbers, CDR, CDG, and CDB. So it's going to be using these 3 inputs to set our color. The other thing we want to double check is what class of attribute we're creating. So the class is a point attribute, and that's what we want. We could also set it to be primitive or some of the other ones that we'll talk about a little bit more later. And we want the type to be float. That means it can have a decimal value, like 0.1, 0.2, whatever. So let's just put in some values here. Let's do 1 in R. So where we actually want to put in our value is not in the default set of numbers here, but in the actual value. So this is the value that we're giving to this. So if we put in 1 here, we can see that we've got 1 in red and 0 in green and blue. We could do 1 in red and blue. We got magenta. Cool. But what if we want a different color for each of these spheres? Well, what we can do is we can create an attribute randomize and randomize this color value. So I'm going to just type random and we get attribute randomize. I'll drop that down here. And immediately we get random colors. And the reason for that is the default attribute that it gives you for the attribute randomize node is actually CD. That's the color value is their default. And one thing to note about the attribute randomize is you don't actually need this attribute create node in advance, because if the geometry doesn't have the attribute that you're specifying in the attribute randomize, it'll create it for you and set a random value. So what it's doing is it's taking these 3 individual values and it's randomly selecting a number between 0 and 1 for each of red, green, and blue. If we were only interested in randomly selecting between 2 different values, we could change the distribution from uniform continuous to 2 values, and it's going to choose a value of between 0 and 1, and the probability of value B is 0.5, but we could change the probability of it being white to 100% or 0%. And so that could be an interesting way to create an effect where you're transitioning between sort of 2 random states. So instead of randomize the color, we could randomize something else. Let's try to randomize the scale of the spheres. And the built-in attribute that Houdini recognizes for scale is called p scale, all lowercase. And here we go. So it's randomly choosing between a scale value of 0 and a scale value of 1. Now, in terms of the dimensions, we actually only need 1 dimension. It's just a single value. And we don't want 2 values. We want, again, back to that default of that continuous spectrum. So here now we're choosing a random value between 0 and 1. Let's change that a little bit. Let's go from between 0.2 to, whoops, the max value 1.2 or something like that. So now we've got a different distribution. So that's nice, but we can go beyond these regular attributes like scale and color and orientation and point position. And you're probably curious how to figure out what these common attributes are. So if you just go into the documentation and search for geometry attributes, you can find a page, geometry attributes, that lists a whole bunch of common attributes like P for point position, N for normal direction, lowercase v for velocity, a bunch more. You can find force and torque and orientation, CD for diffuse color, etc. But maybe we don't want to use one of those existing attributes. We want to make up our own, and we're going to call it something like growth, because we're interested in a growing nanotube. So that didn't do anything yet because we have to tell Houdini what we want it to do with that growth attribute. So let's go back to our curve. Just view our final curve here and see if we can tell it to use the growth attribute in this carve node. So first off, I'm just going to remove this animation here. I can control shift left click here and control middle mouse click, and that's just going to set it back to the default value with no expression or animation or anything like that. And then above that, we're going to do our attribute create. And we're going to call it growth. And now, instead of having a different value for each point, what we want to have is one global value for the whole curve. So we're going to change the class to primitive. And the primitive, because there's only one curve, it's going to have a single value here in this geometry spreadsheet. We can see that we have this growth attribute with a default value of 0, and that's just a single value for the whole curve. Okay, and then by default, just so we can see that something's happening, we can put in a initial value of maybe 0.2 for our growth value. We can see that that data is stored here at 0.2. But how do we get our carve node to use that? Well, let's ask ourselves again, what do we want? We want the carve node to get the growth attribute here that's stored in this primitive curve and use that as this second u value. So we want this to match whatever value is here. So how do we pull that data out of our geometry spreadsheet and use it here? Well, we can use an expression, and there's an expression to get primitive attributes, and that's just called prim. If we do open parentheses, we can see what it's looking for. So this is going to return the value of a primitive attribute. So first it wants to know which geometry node to look at that has the data. Well, the carve node has the data. It got passed down from this attribute create to itself. So look at your own self. And the way to say look at your own self in these Houdini expression language is just 0. It's kind of like in programming, you use the word self, kind of similar. Can you hear somebody doing weed whacking? I mean, now it stopped. Now it started. Okay, so the next value it wants is the primitive number. And well, we only have one primitive. It's primitive 0, so we'll put in 0 here. Hey, expressions are easy, aren't they? All right, next it wants a string, which is the name of the attribute that it wants to pull the value from, and that's growth. So in quotes, we'll put in growth. Make sure we spell it correctly. That's a common source of errors. And then the final value is if the attribute has multiple parts, like the color has 3 parts or point position has 3 parts, what index of that do you want? Well, this only has 1 part. So again, starting at 0, we want the first part of it, which is index 0. So another 0 there. Okay, and we'll hit enter. And we'll also click on here to toggle between the expression and the value that it's returning to make sure that it's pulling that in properly. And it is 0.2. And to confirm that, we could go back up to our growth here and change this value. Whoop. And indeed, look at that. Then what we could do is we could key this, Alt left click to set a key, and then go to frame 24 and 0.8, something like that, and key it, and then rewind and play. Hooray, we have animation. Okay, so you might be thinking, big deal. What we've done is created this much more complicated scenario to do exactly the same thing that we had before when we had the key just on the carve node itself. You're right, but the point is we've kind of, by separating the data from what the data is being used for, we can do much more interesting and complicated things with it instead of just the simple scenario of having the keys on the carve node itself. And one benefit of that is that if we had another effect that wanted to use the same data, we don't have to set up those key values 2 times. We can have this growth attribute stored once and use it in multiple places. Maybe like this polywire, we could do the wire radius times the, just quickly put in here, growth 0 there, and if we view our proxy over time, if we zoom in, that radius is growing because it's also using that same growth attribute. So you're using the same data in multiple places. So that's one application and one reason why you might want to separate those things out. So instead of keying this growth attribute, for example, we could set up an initial random value like we did with the other scale attributes, for example. So putting down attribute randomize, we can create the same thing, growth, make sure that it has 1 dimension, that it's a primitive attribute here. And we're going to set a random value between 0 and 1. Most effects that you're going to want to create might have some element of randomness, so it's important to understand. And when we're generating random values, there's an important value called a seed. And in the attribute randomize node, it's under options. We can see the global seed. The global seed is a number that determines what your output random value is going to be. And this is a number that does 2 things. One, if you don't really like the random value that it gave you, you can change the global seed and it's going to give you a different random number. And even small changes in the seed will create completely different results in your random value generation. So that's the first thing, is to mix it up a little and allow you to create some different results. The second reason for this seed is that it keeps the randomness consistent. That might sound a little counterintuitive, but what it means is that if you use the same value as I do, let's say 2021, assuming that you have kind of the same version of the code that's doing this random number generation, then it should produce the same result. So if you put in 2021, does it give you the result 0.841865? So your randomness shouldn't depend on when you view the file or on what computer you open it up on. So this seed is important to watch for. All right, for the next step, I want to do something even slightly more complicated than what we've done so far. So instead of creating one random value called growth, I want to create two random values, one for the starting point of this growth curve and one for the ending point of the growth curve. And then we're going to interpolate between the beginning and the end and let the curve grow that way. So, and also I'm just going to take off this polywire thing here because, what was that? 4. So let's get rid of this growth, and we're going to create two randomized nodes. One we're going to call start carve, and again that's going to be only one dimension, so just a single value, and that's going to be a primitive class. And we could actually copy and paste this node. I'm just going to call this start carve random. And we're going to copy Control-C and paste Control-V and just stick that back in the same flow here. And we're going to call this end carve and make sure that our attribute is called end carve. Okay, and now you can see that the end carve and the start carve have been created here on the primitive. They're alphabetically sorted, so that's why end comes before start. And you'll notice that they have the same value. So what we probably want to do is go into the options and mix up this global seed a little bit, something, so that we get two different values for our start and end. What I want to do now is I want to start the curve growing somewhere between the bottom. So let's say maybe a very small value, 0.01, and halfway along, 0.5. And the end carve, we're going to start at 0.5. And we're going to go up to 1. So basically this is going to start in the lower part and end in the upper part, as you might expect. So how in the world are we going to get this carve node to use both those pieces of data? I'm just going to remove this expression by Control-Shift left clicking here and Control middle mouse clicking to get that default value back. So we know that we could use that same expression to pull, for example, the start carve, but then how do we animate that up to the end carve value? That sounds like a very complicated expression, and indeed if we tried to put that all into this little box here, that would be a pretty complicated expression. But if we're thinking about using complicated expressions, probably what we want to do is use VEX. VEX is a coding language in Houdini that looks a lot like the expressions that we've been doing so far, but with a few important differences. One difference is that we can have multiple instructions, each on a separate line. It's perfect for little mini operations, or for when you want to do an operation and there isn't already a node that can do that exact thing that you want to do. In fact, I find VEX so convenient that even when there is a node that does the thing that I want to do, for example, the attribute create node, often I just use a little VEX snippet and replace that functionality myself. So where do we write this VEX? Well, we write it in a specific node called a wrangle. Tab wrangle. And you'll notice that there's a bunch of different kinds, but they're pretty much all the same with very minor differences. We can basically just create the attribute wrangle and set those differences and settings ourselves. And it's called an attribute wrangle because most of the time what you're doing in this VEX code is messing around with attributes like we're going to be doing here. So let's put this in here above the carve, between the end carve and the carve node itself. So in this wrangle we have a text box here, and this is where we write our VEX expressions, they say, our VEX code. So first let's try to do something that we've already done, creating a new attribute. So let's create an attribute called growth like we've done before. So let's type growth. And in VEX, you have to end every instruction with a semicolon. So we'll put a semicolon here, and then by clicking outside the box, it's going to try and compute that. And we get a big error because it doesn't know what growth is. What is growth? I don't know about this growth. Well, at the very least, when we're creating a new attribute or new variable, we have to specify what kind of data it is. And remember when we were creating that growth attribute, it had to be type float. A float is a value with a decimal point, or it can have a decimal point like 0.3 or negative 0.9 or 100.7. So we're going to type float growth, and now it stopped complaining. And we want to give it an initial value like we did in the attribute create. So we're going to give it the value 0.5. And to do that in VEX, we use the equal sign. So put a space equals 0.5. And basically what that's reading is this float value called growth is now equal to 0.5. So let's see if this growth value is stored in our geometry spreadsheet. It doesn't appear here in the primitive spreadsheet. Did we specify what kind of attribute it should be? Well, we're saying that it should run over the points. And what this is basically saying is for every single point, do these instructions. Or, contrary, if we want to do for every primitive, do these instructions. But you can see that even when we run over the primitives, it's not showing up in our geometry spreadsheet. It's not showing up in points nor primitives. What's going on there? This is because we haven't actually created an attribute. We've just created a local variable. This variable that's storing a value just within the scope of this node on its own. As we go down into downstream nodes, that information is lost. So if we want to use that information later on, we want to make sure that it's an attribute. So you need to tell Houdini in this VEX language that this is an attribute. And the way that we do that is we just give a little symbol, the at symbol, short for attribute, so it's easy to remember. And if we put a little at the beginning there, now suddenly we get that growth attribute stored in our geometry spreadsheet, and it's stored on this curve primitive. So we're running this over our primitives, which means that in this case, because we only have one primitive, we are just running it a single time. But in some instances, you might have lots of primitives and lots of points, and you still only want that VEX to be evaluated a single time. And in that case, you can use the detail type. And that's going to be storing this attribute as a detail attribute, which is this fourth button here. And that's a single piece of data for the entire set of geometry, whatever that is, your entire object, if you want to think of it that way. It's definitely worth knowing that that's available to you. So I'll change this back to primitive so that we're storing that growth value on this primitive. And so just very quickly, there are other types of data that we might want to store if you wanted. So an integer is a whole number like 1, 2, negative 10, 133, that sort of thing. So we might want to have a variable called count and set that to 12. If we want to have something with text characters, that's called a string. And so we could give it a name, for example, carbon or something like that. And that has to go in between these quote marks. And finally, we could have something like a vector, which is a set of typically three numbers together, float numbers most of the time. And we might want to call that direction. And the way that we specify that is with these curly brackets. So we might go 0, 1, 0. And that's going to be a direction in X, Y, and Z. So we're going to be going straight up in the Y direction. That's what that vector would correspond to. You could also use that for point positions and that sort of thing. And remember, these are not going to be showing up in our geometry spreadsheet because these are not attributes. These are local variables that won't exist outside of the scope of this attribute wrangle. So if we wanted to make them attributes, then we would have to convert them to attributes like so, at. And now we can see we have direction, 3 parts to that. Then we've got count, name. And one more thing, when people are creating attributes, there's a shorter convention that people typically use, which is just that first letter of the type and no space between them. So f at growth means a float attribute of that's called growth. We do I for an integer, S for a string, V for a vector, and those are all valid, and that hasn't changed our values at all. Okay, so let's get rid of these extras here. So we have a float growth. Thinking about our animation, what we want is that growth to be changing over time. We want to animate this with keyframes or an expression instead of just this static 0.5, and it's always 0.5. All we need to do is make a custom parameter, and that sounds complicated, but it's actually very easy. So instead of this value here, what we want to put in is a channel reference, or a reference to a parameter. And we've seen that before when we were referencing other parameters in expressions. So we do ch for channel, and this is going to return the value of whatever name we want to do. We can type growth to keep it consistent with what we're actually looking for. We can call it whatever we want. My growth, if we wanted to, doesn't really matter. Close brackets, make sure we've got those parentheses around there. Now growth evaluates to 0 because this parameter doesn't exist. We have to make it. How do we make it? It's actually really easy. All we have to do is click this button here, boom, and now we have a new slider down at the bottom that will feed in this value into this attribute growth. Why did this button do that? This is just basically creating new parameters for each unique call of ch. But basically it's saying it's an easy way to help us out here. Anytime we're looking for a parameter that doesn't exist, just make it down below. And if we wanted to change some properties of this, we could go into here and edit the parameter interface. I'm not going to get into that, but there's definitely more things that you can do with this. But the defaults are actually really nice because it's a slider from 0 to 1, and that's kind of what we're looking for. And of course, we can now animate this. So we could do Alt-click to put down a key, go to frame 48, something like that, and go up to 0.876 or whatever we wanted to. And now you can see in the geometry spreadsheet, if we hit play, that number is changing over time. It's not affecting our carve yet because we haven't set that up again, but we're well on our way. So again, this is really the same as what we had before. We're just doing this in a slightly different way. But because we're doing this in this VEX wrangle, we have so much more power to do a lot of really complicated and interesting things with it. Any kind of mathematical operations, or the sky's the limit. Okay, so let's bring it all together and bring in this start carve random value and this end carve random value. And instead of this growth slider being the final value for what this carve node is using, we're going to be using this as kind of an interpolation value. So what that means is when this growth is at 0, we're going to be given the start carve value. And when it's up at 1, we're going to get the end carve value. So we're kind of be sliding between this value and this value. So that kind of interpolation is called linear interpolation. And there's a mathematical formula which you would look up on how to do, and we could put that mathematical formula in here. But here we can just use a built-in function called lerp, short for linear interpolation. So this is going to be asking for 3 values. So we've got the starting value, the ending value, and sort of the amount to go in between those two. Great. Well, how do we access the first value, which would be the start carve? Well, we could try that prim expression sort of thing, but because we're in VEX, it's actually very easy. All we have to do is reference it with @startCarve. And because this is sort of the first time that this VEX bit of code is seeing this value, we also want to specify the type that it is. So we're going to do f for float. So we've got f @startCarve, f @endCarve, that's the second value, and we have growth. And because we've already specified what kind of attribute, what kind of data it is, we don't even need to put the type character at the beginning of it. There we go. So now what do we want to do with this value? Well, what we want to do is we want to store it so that the carve node can use it. So we're going to be storing it into a new attribute. So I'm going to call it f@carve because we're going to be using it in the carve. There we go. So now we have this new carve attribute, and currently its value is 0.7 something, and that's because our growth value is at 1. But if we rewind back to 0, our carve value is now 0.15 something, which is the same as our start carve. So now we're interpolating between start value and end value. Fantastic. And come to think of it, we don't actually need this growth attribute anywhere else other than within this little bit of VEX code. So we can actually convert this to a local variable just to keep things a little bit tidier. Just get rid of those @ symbols. And now we've got growth disappears from here because it's just kind of extraneous temporary information. And all we really care about is this final carve value. And of course, the end carve and start carve still get passed down because we created them higher up in this chain here. So I'm going to call this wrangle calculate carve. And of course, what we ultimately want to do is we want to access that carve value here using an expression in our carve node. So remember, we did prim 0 to say, look at your own self. Then we want the primitive number. There's only one, so we do 0. The attribute name is carve, and it only has one index because it's just a single value. And so we're going to do that. And we'll just click here to make sure that it's pulling that in. Super, super. And there we go. Now we've got this attribute start carve defining where this curve is starting. And we've got this random end carve value defining where it ends. And if we wanted to re-roll the dice on that, we could always just change this global seed here. And you can see that this is changing very rapidly, but we still have going from the beginning to the end. And once again, this looks overly complicated for doing this with a single curve, but if we had dozens or hundreds of curves, this is going to scale really nicely, which we'll see in a later video. One thing we might want to do, since we talked about this last time, is this growth animation here. If we check the animation editor, we want to make sure that this is linear. So I'm just going to select the curve segment here and change this to linear so that we have true linear interpolation between these two values. But this is the nice thing about having this driven, not just with some fancy mathematical expression, but a user-controlled a slider here so that we could animate this in any way we want. We could have it going all the way up to 1, key that, and then have it come back down to halfway in between or something like that. Let's just have the value here. So we can have it go up and then shrink again. So you can do whatever you want with that animation, but I'm just going to have it go from 0 to 1. Actually, one other problem that I've noticed here, if we look at this actual curve, look at the points of this curve, this is a NURBS curve, and the way it's set up is that there's not uniform distance between these CVs. So as it grows, it's actually not going to be growing exactly at a constant rate because the spacing between those points is going to be different. So the way that we could solve that and make sure that this is just a nice, consistent growth rate is putting down a resample. So I'm going to do that. It doesn't matter too much where I do it as long as it's above the carve, I think. But I'm going to do it sort of up at the top here. And I'm going to put down a resample. And I don't need it that tightly spaced, but I might do something like 3. And now you can see that these points are evenly spaced. And when we get our final result here, I might switch it back to the proxy so it's a little bit quicker. We should have nice even growth. So I told you this was just going to be a little bit of code. Indeed, all we had to write was these 2 little lines. So hopefully that wasn't too bad, and it gave you a little bit of insight into the power that something like VEX can do to broaden the possibilities within Houdini. If you are serious about Houdini, I think it's really worth your while to learn some more of the basics of VEX. I'm not going to be getting into much more today, but I think it's really worthwhile and powerful to learn. The code really isn't that bad to learn unless you're wanting to get into something like matrix manipulations and other complex operations. And even then, it's the conceptual mathematical side that's more complicated than the actual code itself. Okay, before we finish the lesson, let's go ahead and fix that problem that I teased in the last video and at the beginning of this video, and that's to fix these dangling things at the bottom here. So what I'm going to do is I'm going to change the growth rate down to something like 0.1, so that's very slow growth. Even that's a little bit, maybe 0.03, 0.04. There we go. So now you can see a little bit more clearly what's happening here as it's growing. So what I want to do is on frames where there are these extra bonds sticking out from the below, I want to blast them away. I want to delete them. Initially for the actual animation, I found a very convoluted and not that effective solution for this. But while I was preparing these tutorials, I found a much more elegant and functional version. And that's what we're going to be exploring today. So the way that we're going to do it is basically a check. And what we're going to check is whether each bond is connected to 2 atoms or 1 atom. Because all of the other bonds, all of the bonds in our final geometry should be connected to 2 atoms. But if it's only connected to 1, that means it's sticking off the end and we can get rid of it. So to find those connections, basically what we can do is we can I'm going to give myself some more space to work here. So I'm going to be coming off this path deform here, and I'm going to be creating a connect adjacent pieces. And if we look at that, we might not see anything at the beginning, and that's because our search radius is too small. But as our search radius goes up, we can start to see these extra lines connecting these various pieces. And actually what I'm going to do first is to delete the geometry with an add node. I'm going to bring that ahead. I'm going to delete the geometry but keep the points. And I'm going to template this here so we can kind of see what we're dealing with. In the connect adjacent pieces, I'm going to do just connect adjacent points here. And whew, that's making a lot of connections. All we want to do is look at a smaller search radius here. And basically, this is the same sort of thing as what we were doing way up at the top here when we were making bonds. Here we go, bonds. But now because we have the bonds to start with, we have points that represent the middle of each bond, which we didn't have before. And now if we have a search radius that's only half of our bond length, we can make this sort of bond point connect to all of the surrounding atom points. So we only really need like 0.4, something like that. And you can see that each of these bond connections here and here, here and here, but when there's a dangly, it's only connecting on one side. This is going to make a little bit more sense once we actually use our VEX to check for this. So I'll put down a wrangle. And I'm going to call this check for Danglies. Okay. So we are going to run over each point, and what we're going to check is how many primitives it's a part of. There's a function for that called, I'm going to have to look it up, point prims. So it returns the list of primitives containing a point. We haven't dealt with lists yet, but that's basically a whole bunch of data values stuck together into a list or an array you might be familiar with. So which geometry do we need to look at? That's a very common thing. It's look at your own self. And then what we want to look at is which point we're evaluating. Now, which point do we want to do this check for? We want to do this check for each and every point. And that's one of the real benefits of using this wrangle, is because we're running over each and every point. If we look at the geometry spreadsheet, oops, it's going to return an error because we haven't finished our code here. We want to look at this point and this point and this point and this point. So there's a special attribute that each point has that's not listed here. It's implied, and that's called @ptnum. And that's the same as the index. So this point is going to have the @ptnum value of 7, and this point is going to have the @ptnum value of 13, etc. So because we're looking at each point, we just basically want to say, look at the same point that you're looking at. So you might be wondering, why do they even ask for this? Why would you not want to look at the point that you're looking at? Well, there's a couple of reasons. Maybe you're doing some expression or code where you always want to look at point index 0, the first point in the geometry. Or maybe you always want to look at the next point relative to the one that you have this point number value for. Maybe you want to look at point num plus 1. And then when you're evaluating this point, it's going to be looking at the next value. So there's a variety of different scenarios why you might not just want to use this @point num, but it's very common to put something like that in a function like this. Basically, all this is doing is returning a list of the primitives that each point is part of. So if we're looking at, turn on our point numbers here. If we're looking at 0.841, If we turn on display primitive numbers, whoops, if we look at 0.841, it's going to return a list with the numbers 807 and 666. Those are the primitive indices. And when we're evaluating 912, it's going to return 806 and 809. And when we're evaluating point number 268, it's going to return a list with three values, 804, 806, and 805. But if we're looking at point 913, it's only going to return a list with just the single item of 805. So what do we do with that information? Basically, we don't care what these numbers are. We don't care that it's 809 or 804 or whatever. We just want to know how many of them are there. And that's when we want to look for the length of the list it's returning. So I'm going to use a function called len, which returns the length of the array, and wrap that all the way around this point prims function. So what this is going to return is an array, and then what the whole thing is going to return is just the size of that list. And I do want to store that. So what do we want to store that in? Let's store that in an integer value called count or length or size. Maybe we'll call it size. So remember, once again, integers are counting numbers. This could be 1 or 2 or 3. And indeed, those are the numbers that it's going to be. So what do we want to do with this size value? Now remember, there's a few different possibilities for what it could be. If the point is an atom, the size is going to be what? 3, right? Because it's always going to be connected to 3 primitives. If it's a bond that's connected to 2 atoms, that size is going to be 2. But if the size is only 1, that means it's a Dangly. So we can write that. We can say if, and we're going to do open parentheses, size equals 1. And here's another common source of errors. When we're assigning a value like we've done before, we use a single equal sign. But if we're checking for equality, if we're saying, does this equal this value, then we need to use 2 equal signs together, equals equals. So we're saying if the size is 1, if it equals 1, then do something. So we're going to do open curly brackets for then do this and close curly brackets, and that says we're finished doing what it is that you want to do. So inside here, this is what to do if it's 1. Okay, that means it's a Dangly. So I just want to put that point into a group. So there's a special syntax for putting something in a group. It's very much like an attribute, but with the group prefix. So, and it's an integer value. So we'll do I at group underscore and then the name of our group. So we'll say Danglies. And we're going to assign that a value of 1. And that means that if the size is 1, that means it was only connected to the 1 primitive, then put it in a group called Danglies. All right, so now we've got this group called Danglies. And remember, groups, if the value is 0, that means it's not in the group. If it's 1, that means it is in the group. We could sort by clicking on it, and we can see that we have, what is that? About 10 points that we found were essentially Danglies, and that matches up with what we would expect because we can see that we've got about 10 here that should be in that group. Now, I haven't explicitly said that if the size is not 1, don't put it in that group, assign it a value of 0, but that's just kind of implied. So all it's saying is if the size is 1, put it in the group, otherwise don't put it in the group. That's sort of implied. And now this is really great because it doesn't matter which frame we're on. Let's say we're on a frame where there shouldn't be any Danglies. You can see that the group is empty, but on a frame where there are Danglies, there are some in that group. And those points are going to be changing all the time. It's not always the same group. It's a dynamic, ever-changing sort of thing. So it doesn't matter what kind of input geometry we have, it's always going to evaluate properly, which is great. So can we just blast this group then? We could put down something that says blast and check the group Danglies. And so now that's going to delete these Danglies, but that doesn't really work for our original geometry. We've kind of messed up this network flow where we've got this side branch. And I don't want to put all of this stuff back in line with the main branch here because we're doing some destructive operations. We're deleting the geometry, we're making new primitives, and I don't want to mess with my actual geometry. So the question is there a way to somehow kind of transfer this group back to this main path of geometry? And it turns out there is, with a node called group transfer. So we can drop that down and put this into the group to transfer groups to, which is our original geometry stream. And I'm just going to disconnect this blast by grabbing it and shaking it like a dog with a chew toy. And this is going to ask for the geometry to transfer groups from. That's this group here. And basically we want to transfer the Danglies. We can uncheck the other stuff. So it's going to transfer the point group Danglies back to our original geometry. And now if we put this blast back in, hey presto, look at that. Now we've got those points and the associated primitive bonds getting blasted away. And so if I'm going to turn off our point and primitive number view here. So now doesn't matter what frame we're on, we don't have any of those dangling bonds. Amazing. So lots of explanation, but actually not too much work to fix that problem in a fairly elegant way, I think. So thank you so much for joining me for another part of this Houdini nanotube tutorial series. I hope you had some fun with VEX. If you're not completely vexed, then I encourage you to leave a thumbs up. Leave a comment if you like, maybe share this with a friend. Feel free to ask questions, and I hope you'll join me in the next video. If part 6 is published, you can join me by clicking on this video thumbnail over here. Otherwise, stay tuned for more. Thanks again for watching. I'll see you next time.